Good afternoon, students. So far, we studied about DC circuits. In the next three chapters, we will study AC or alternating current circuits and circuit analysis. Actually, it is an introduction to AC. In more detail, you will study in other courses, but in this in ECEN280, we just give a brief introduction about AC circuits. For example, in this chapter, we will study about sinusoids, phasor relationship for circuit elements, impedance, what is impedance, admittance, and Kirchhoff's laws in frequency domain, and how do we combine impedance. Okay, as I said earlier, before, for example, if I have a DC circuit, here a resistor and capacitor, in the previous chapters, we tried to find the transient response, the steady state response, and so on. But now, what if the source changes from DC to AC? How do we analyze? How we find the voltage V of t and the current I of t across the current through the circuit and the voltage V of t across the capacitor. So we need to have some methods of analysis of such kind of circuits if the source is AC. So as you know, AC inputs are most of the time they are sinusoids. Sinusoid means it is either a sine wave signal or a cosine wave signal. And for example, here a general form of a sine wave is represented by V of t is equal to Vm sine omega t plus phi. Vm, we call it the amplitude or the peak amplitude of the signal, and omega is the angular frequency in radian per second, and phi is the phase shift or the phase factor, and f is the frequency. We know that t is the fundamental period, 2 pi over omega, and the frequency is 1 over t, and omega is 2 pi f in radian per second. If you see here, if I plot the voltage as a function of omega times t means now the angle. Omega times t will give me the angle in radians. I have this kind of waveform, which is periodic with 2 pi. The period is 2 pi. And if I plot it as a function of time, I have this. And one full period means it go up, maximum it crosses 0, and it comes back to 0, and then it will repeat itself. So this is again the previous function, and this is V of t Vm sine omega t. This is a maximum Vm. It starts from 0 and goes up, and it crosses pi, and it comes back to 2 pi, and this will repeat. This plot is as a function of omega times t, which is an angle. And if you see the dotted line, I have a similar sine wave, but shifted to the left by an angle phi. So we call this the dotted waveform is leading the solid line waveform. So V2, the dotted waveform, is Vm sine omega t plus phi. Now, when we analyze sinusoids in a circuit, the signals, that means the voltages and currents, we write them as in the form of, for example, cosine or sine. So we have to change to the form of all the currents and all the voltages to cosine form or to sine form. In this, for example, in this course, we change everything to cosine. So we need some trigonometric identities. For example, here we have a sine A plus of minus B. As you know from your math course, it is sine A cos B plus or minus cos A sine B and so on. And for cosine A plus or minus B cos A cos B minus plus sine A sine B. So we use these trigonometric identities to change, for example, from sine form to cosine form or from cosine form to sine form. For example, minus sine omega t can be written as sine omega t plus 180 degree. Minus cos omega t is cosine of omega t plus 180 degree, and so on, using this relation. Because sine omega t plus 180 means sine omega t cos 180 plus or minus cos omega t sine 180. Sine 180 is 0, so this part will be 0, and cos 180 is negative 1, and it will give you minus sine omega t. So you can check this for example, these relations using these trigonometric identities. Now, if I have two voltages, one voltage V1 of t, A cos omega t plus phi, A is the amplitude and phi is the phase, and another voltage V2 of t, B cos omega t plus theta, it can be current also. Now, we say if beta equals phi minus theta is positive, we say V1 of t is leading V2 of t by phase angle beta. Otherwise, if phi minus theta is negative, we say V1 of t is lagging V2 of t by an angle beta. And the same also, if alpha is equal to theta minus phi is positive, we say V2 of t is leading V1 of t by an angle alpha theta minus phi. And similarly, if theta minus phi is negative, we say V2 of t is lagging V1 of t by an angle alpha, and so on. Now, most of the time, if I have cosine and sine form like this, A cos omega t plus sine omega t, we change it to cosine using this trigonometric identity. So this is equal to C times cos omega t minus theta. What is C? C is the square root of A square plus B square. And theta is tan inverse of B over A. I have here one simple example. Let's say I have 3 cosine omega t minus 4 sine omega t. What is A? A is 3. B is negative 4. So C will be the square root of 3 square minus 4 square, which is 5. And the angle theta is tan inverse of minus 4 over 3, which is minus 53 degree. And I have minus minus, this will become plus. And most of the time, as I said, the x-axis is cosine, and here the y-axis is sine. So the angle, for example, from this form, C is a vector from the origin to here. This is the magnitude, the amplitude, and the angle is minus theta, because most of the time we start measuring from the x-axis. Starting from the x-axis, we measure counterclockwise positive. If we measure clockwise, it is negative. So this example will become, if I draw it in this axis, in the cosine and sine axis, or in the real axis and imaginary axis, I have an amplitude 5 and angle 53 degree, positive 53. Okay, now let's see this example. Given 5 cos 4 pi t minus 60 degree, calculate the amplitude, phase, angular frequency, period, and so on. Very easy, yeah? Here it is straightforward. 5 is the amplitude, the phase angle minus 60 degree, and the angular frequency is 4 pi radian per second. The frequency is, we can find it, omega is 4 pi, so f is 2 and the period is 0.5, 1 over f. If, for example, as another example, if I have I1 minus 4 sine 377t plus 25 degree, I2 this, does I1 lead or lag I2? Okay, so to do this, what is the first step? The first step is we need to change them to the same form, either sine or cosine. Okay, we usually change to cosine form, so we change the first one to cosine. I have here minus first, using this identity, sine omega t is equal to cos omega t minus 90, and sine omega t plus 180 is minus sine omega t. So firstly, I change it. I change this minus sign. I add, for the minus sign, I add 180 phase shift. So I have 205 degree. Then when I change it to cosine, I need to subtract minus 90, and I have this. So this is I1. So I compare it with I2. Okay, remember they have the same frequency. This has 5 amplitude. This has 4. 377, the frequency in radian per second, 377. Now the angle, the phase angle is, this is 115, this is minus 40. Therefore, I1 leads I2 by an angle of 115 minus minus 40, which is equal to 155 degree. Or I2 lags I1 by phase angle of 155 degree. The most important thing here is we need to change them to the same form, to sine form or cosine form. So here in this exercise, we change them to cosine form. Okay, so phasors are usually analyzed in the complex plane by the real axis and imaginary axis like this. The imaginary axis, or the j-axis, we call it. Remember, j is a complex number which is equal to square root of -1. So the amplitude is from the origin to at this point. At this point, for example, I have r, which is the radius, and the angle is phi. So I can represent any complex number z in terms of its real part x plus in terms of its imaginary part y. So z is x plus jy, or in terms of an angle, r cos phi plus j sin phi, where phi is the angle between the x-axis and the radius r. This is called a rectangular form. We have polar form. Polar form, z is equal to the amplitude r at an angle of phi, or exponentially r e raised to j phi. And phi is tan inverse of y over x. And we usually use the rectangular form for addition and subtraction because it is very easy to add the real part together and the imaginary part together. And we use the polar form for multiplication and division. For example, this exercise, multiply 5 plus j2 times -1 plus j4 minus 5 at an angle of 60 degree. So we need to do direct multiplication here. You can follow the steps. So 5 times -1, 5 times j4, and so on. And after we do this process, we finish this part and change it to real part and imaginary part. And then this one is in polar. We change it to rectangular. It will be 5 cos 60 degree plus j sin 60 degree. And then we add the real part together, the imaginary part together, and finally we have this. Okay, what about this one? To do this, first we need to change this polar form to a rectangular form. Okay, 3 at an angle of 40 is polar, and change it to rectangular and add the real part together, the imaginary part together, and make rectangular form. And then, because it is division, change the rectangular form to polar form. and you make the division. After you finish the division, you have polar form here, change it to rectangular and change this to rectangular and add them together. So for addition, subtraction, we use rectangular form. For multiplication, division, it is better to use polar form. It is easier to use polar form. Okay, this is some of the rules of, you see, addition, subtraction, multiplication, addition. If I have two complex numbers here, x1 plus jy1, x2 plus jy2, addition, add the real part together, the imaginary part together, subtraction also similar. Multiplication, better to do it in polar form. If I have for z1, r1 at an angle of phi 1, r2 at an angle of phi 2, multiply the two, and I have r1 times r2, add the phases phi 1 plus phi 2. Division, r1 over r2, phi 1 minus phi 2. Reciprocal, if I have z is equal to r at an angle of phi, it will be 1 over r at an angle of minus phi, and so on. And here, Euler identity, very important Euler identity. Euler identity is E power of plus or minus j phi cos phi plus or minus j sin phi. And complex conjugate, very easy. So the positive j will change to minus j and so on. And square root of z means the square root of the magnitude part, and the angle will be divided by 2 because z is equal to r times e raised to j phi. So when we make the square root, the phase angle will be divided by 2. Okay, so if I have any voltage v of t Vm cos omega t plus phi, we write it in phasor form. In phasor form, we write it as Vm e raised to j phi. This is the phasor form or the polar form. Phasor form means frequency domain, and this is time domain. Okay, this is time domain representation, and this is phasor domain or frequency domain. In the phasor domain, we have the amplitude and the phase angle phi. In general, how we change from phasor domain to time domain. Okay, if I have a certain signal Vm e raised to j phi, so we multiply by e to the power of j omega t and take the real part. The real part of Vm e raised to j phi times e raised to j omega t will give me Vm cos omega t phi. So by this way, I change the phasor form to time domain form. If you see this in phasor form, Vm e raised to j phi times e raised to j omega t, that means Vm is not changing because the magnitude of this is always Vm. So when time is changing, so it is the vector is rotating. The vector is rotating. The radius is constant Vm. And if you project this on the real axis, you will find the wave Vm cos omega t plus phi. All right, so if I have a phasor form, for example, the voltage V, where I represent it Vm at an angle of phi, the current I am at an angle of minus theta, for example. This is an example. This is graphically, if you show here, I have real axis here, I have imaginary axis. Then Vm at an angle of phi is the amplitude is Vm and the angle is phi. And I am at an angle of minus theta. Remember, minus theta is from a real axis. We go to clockwise. So minus theta is this. So it will be like this. So again, here I have time domain Vm cos omega t plus phi and phasor domain or frequency domain Vm at an angle of phi. And here I have sine Most of the time here our reference is cosine, so first we change this to cosine. When I change it to cosine, it will be cos omega t plus phi minus 90 degree. So the phasor form will be Vm at an angle of phi minus 90, and this is Im at an angle of theta, and this one Im at an angle of theta minus 90. Okay, transform the following sinusoids to phasor form. Very easy. Now this is first thing we have to make sure it's cosine. Here it's cosine. Straightforward. The first is 6 at an angle of minus 40. What about the second one? First we change the because I have minus sign. I change it to cosine. Okay. So I change the sign to cosine and the minus also. For the minus, I have sine of A is equal minus sine of A is equal sine A plus 180. So we add 180 for the minus and minus 90 to change it to cosine, and we have 4 cos omega cos 30t plus 50 plus 90 degree, which is 140 degree. So it will be 4 at an angle of 140 degree. Okay, transform this is another example. Transform this phasor to sinusoid. I have minus here, so I write it first in terms of exponential, like this will be 10 times e raised to j 30 degree times here, because of minus, I have e raised to j 180. So 180 plus 30, it will be 210. So finally, I will have 10 cosine of omega t 210 degree. And this one, first we need to multiply j times 5, 5j, and j minus j, 12. So 12 plus j5, and we take the magnitude, we take the angle, and we have this. And we can change this to time domain 13 cos omega t plus 22.62 degree. Find the sinusoid corresponding to these phasors. This is a practice problem. It's very easy. Again, you use the previous method and you can have the answer this. You can check by yourself. What is the difference between V of t, the time domain, and the phasor domain? V of t is the time domain is the instantaneous value. That means the value of the voltage or the current at time t. And V is the frequency or the phasor domain representation. V of t is always real. The value of V of t is always a real number. But the phasor form is a complex number. It can be purely imaginary, it can be purely a real number, or it can have both real part and imaginary part or complex number. So phasor analysis apply. Remember that phasor analysis apply when the frequency is constant or when there is two or more sinusoid signals. They should have the same frequency so that we can use the phasor concept to solve the circuit. Okay, now we have here some relationship between time domain and phasor domain. If I have V of t, the signal, okay, in time domain, the phasor will be V at an angle of phi. How does this come? Okay, we can see this. V of t is Vm cos omega t plus phi. Okay, let's say this is V of t. What is the derivative of this? The derivative of this is Vm cos omega t plus phi. So the derivative of cosine is minus sine, and by chain rule, the derivative of omega t is omega. So I have minus omega Vm sine omega t plus phi, and change this to cosine form. So to change to cosine, for the minus verse, I have to add 180 degree. So I have this plus 180 degree, and to change the sine to cosine, I need to subtract minus 90, and I have this form. So this form, when I write it in phasor form, I will have real of omega times Vm, and the angle is phi plus omega t, phi plus omega t times e raised to j 90 degree for the 90 degree. But e raised to j 90 degree means j. So I have j omega Vm e raised to j phi e raised to j omega t. So if I see this in frequency domain, it is j omega times the original phasor. What is the original phasor form for the first, for this one? It is Vm e raised to j phi. So I have this j omega times V, j omega times V. This is for the derivative. So the derivative of V of t is j omega times V, or omega times V at an angle of 90 degree. And the integration is V over j omega. So V over omega at an angle of minus 90 degree. Okay, let's try to solve this we call this integral differential equation, because it is a combination of integration and derivative. So let's try to change it to phasor form and solve this. For I, so I in time domain, it will be in phasor I capital, okay, 4 times I. This is 8, and the integration will be I over j omega. The derivative will be j omega times I, and this one in phasor 50 at an angle of 75 degree. And now what is omega? Omega is 2. Omega is 2 here, so substitute 2, and here also 2, and rearrange this. After you rearrange, you get I into 4 minus j10 is equal to this, and after that we have I, this one divided by this, which we will get like this. This is, what is this form? This form is phasor. So change it to time domain, it will be 4.642 cosine of 2t plus 143.2 degree. Okay, you can practice with this problem. This is also how it's integral differential equation. So we have voltage, and try to solve it by following this these steps. Okay. All right. Now, if I have a circuit like this, for example, how we find the voltage here, the voltage at the output, the voltage across the inductor. Okay. Uh, from the previous chapter, as you know, we can apply KCL here, KCL at node A. Let's say this voltage, the voltage is the source voltage, Vs 20 cosine of 4t minus 15 degree. So V at this node is VA means the voltage at node A is equal to the voltage across the inductor. So VA is equal to V naught. So V naught minus Vs divided by 60 is the resistance, okay, the current leaving this node, and the current leaving and passing through the capacitor C dVo by dt, and the current through the inductor 1 over L integration from minus infinity to T V naught T dt is equal to 0. And this is a combination of integration and derivative. If we do one more time the derivative, we get this, and rearrange this, we get this, and finally we get the second order differential equation. So solving this becomes a little bit complicated or tedious. So how we can be able to solve this? How we can be able to solve this easily? Okay, we can do it. It's very easy to do it using phasor representation, or changing from time domain to frequency domain. So in the next lecture, we will see how we can easily solve such kind of problems. For example, how to find the inductor voltage, or the voltage across the inductor or the capacitor or whatever, by changing the source voltage to phasor form, and changing the capacitor to frequency domain, and also the inductor to frequency domain. So we change everything to frequency domain and we solve it in frequency domain. And of course, later on we can change it to time domain. When we are solving such kind of problems, we can use KCL, KVL, and all the theorems and laws that we studied so far. So in the next lecture, we will study how we can be able to solve such kind of circuits using phasor representation or frequency domain. Thank you for listening to this lecture.